This is the heat and temperature lab. Whoa, right there. Here we go. Our thermal energy. The last one was, okay. Now what you've got are cups 1 and 2 labeled such, and you've got, I'm recording, let me stay close to the thing. You've got a thermometer in each one, so read the temperature off those 2 thermometers in cups 1 and 2. Okay? Okay? Everybody read those 2? Cups 1 and 2, thermometers 1 and 2. Record the temperature. Got it? Let me know. Okay? 1 and 2, you got them?
One of them don't work.
What doesn't work?
What's that? That's what we put down.
Okay. Okay, keep it in the water. Okay. All right, has everybody read cups 1 and 2 temperature and recorded them? All members of every team, right? Okay. Now, pour the water from either cup 1 into cup 2 or cup 2 into cup 1. Mix those 2 together. Pour all the water from one cup to the other. It should all fit. Okay? May have gotten a little close on some of them. Okay? Pour it all in there, and then measure the temperature of the mixture and record that. With either thermometer, it doesn't matter. Okay? When you have those done, okay? Everybody got them done? Pour the mixture, and you've registered the, okay. When you're taking the temperature, make sure the bulb stays in the water. Don't pull it out to do it, because then it's going to be a lower temperature. Okay? So, everybody got that mix done? Okay, move your 2 thermometers to cups 3 and 4. Okay? And, after a while, measure those temperatures. Take a little while for them to equilibrate, but after a while, take those measures. Cups 3 and 4. All right? Be sure when you take the temperature, you can lift it a little bit, but leave the bulb in the water. Has everybody gotten those temperatures? Okay? Has everyone gotten those cup 3 and 4 temperatures? Okay? 3 and 4 temperatures. Everybody measured and recorded. Yay or nay? Don't do anything else. Just record those. Okay? All right. You recorded them? All 5 teams? Everybody got them down? Cup 3 and 4. Okay, you see what the temperatures were? I want you to estimate when you mix these 2 what the temperature is going to be. You see what happened with 1 and 2? Then you estimate what's going to be when you mix 3 and 4. Before you pour, estimate. Make a prediction. Everybody got a prediction made? You may differ from your teammates. I don't care. Okay, wait. Everybody estimate? You got it written down. Okay? Then you can pour the water from cup 3 to 4, 4 to 3, whichever. Okay, not that. Not that. Yeah, these 2. All right. Trying to mess up our procedure. Okay. Okay. Pour 3 and 4 together. Probably pour 4 into 3. And then measure the temperature of that mixture. Yeah. Make sure those are completely empty. In fact, if you want me to use that one, 30 seconds. Finish with that. Okay, has everybody actually taken the temperature of the mixture? Mix 2. Yay or nay? Okay. Everybody taking the temperature of the mix? Okay, now I want to get your impressions. Did you find that A and C, cup 1 and 3, had close to the same temperature?
Yes.
How about 2 and 4? Close to the same temperature?
Yes.
Okay. Now, since the mix from 1 and 2, you know what its temperature was, and you know what the actual temperature of the mix was. Are they fairly close?
Yes.
As close as the temperatures were of 1 and 3 and 2 and 4? They are. Really? I'm surprised.
What made it was off? It was off by 2 degrees.
3 degrees apart. And this is 2 degrees. Okay. Okay. But in general, did you find that the mix 2 was enough different from mix 1, more so than 1 and 3 and 2 and 4? Yes or no? Did you find the difference?
Yep.
Okay. How do you account for that difference? The temperatures were almost the same, but the mixes were not almost the same. They were close, but not the same. How do you account for it? Say again?
Yeah.
I can't hear. I hear something. Someone's saying something. Okay, yeah, one of the mixes was hotter, but the original temperatures were almost the same, right? Aha! It wasn't the temperatures you're averaging, it was the heat, that you worked. So there was more water in 3, less in 4. So I see. Okay. So you don't just average temperature; you average basically the amount of heat, and that influences the temperature. More water in 3 than in 1, and less water in 4 than in 2. So you should have had a higher temperature at the last than you did at the first. Mix 2 should have been hotter than mix 1. Is that right?
Yes.
Yeah, exactly. Even though the original temperatures were close to the same. Right? Okay. Now, I'm going to have to do another pause here to set up for the next time. So I'm going to put this on pause. Now what you have is, okay, zero the scale before you, okay, yeah. Okay, now, what you have are 2 cups. One contains water and one covering it. 2 other empty cups. Take one of your empty cups, put it on the scale, and zero the scale with the cup on it. Okay? And then take the cup of water that you have, put it back on the scale, because the one you zeroed, no, the one you zeroed on the scale, is that the one you zeroed? Okay, we'll zero it again, just make sure. You'll have to wait until it's time for you to do it. Zero, and then pour the water from your cup until the one on the scale is right around half full, a little more than half full. So not much more than half full. Okay? And then measure the mass of the water. Okay, and once you got your mass, take yours off, let another team get there. Okay, everybody understood? Now take your cup, an empty cup, and put over the top of that. Okay, you did. Okay, go on. There's empty scale. Go to the scale. Huh? In gram. in grams. Mass of the water in grams. Okay? Put it on the scale and 0 after you put the cup on the scale. Okay, now 0. Okay? And then get your water over there and pour it till it's right around half full, maybe a little beyond, but not much beyond. Has everybody done it now? You got the mass of the water. Once you got the mass of the water, take one of your thermometers that you have been holding and put it in that water that you got the mass of. Okay? Have you done that?
Yes.
You've already got the water, or you're getting it now? Okay, then put the one that you measured the mass and put your thermometer in. Don't use the other cup, the one you measured the mass of. All right? Well, that wasn't the one I did, was it? Okay, that, you haven't measured your water yet.
Oh.
Okay? Okay. Measure the mass. Now keep them separate. The one that you pour the water from, you can go and dump that water to keep from being confused. Okay? Okay, if you got the mass, the temperature of that water. Some of you haven't got the mass of the water yet. Please get the mass of the water. And then get the temperature of the water. Okay? What's that? Okay, measure the mass. What's that? That's enough. That's good enough. Okay. That's 300. Okay. Determine that and take it and put a cover over it. Dump that one so you don't get them confused. Okay? All right. 0 the scale. Put the cup on it. Okay, has every team gotten the mass of the water, half a cup, and you're taking the temperature of the water? And in between, keep it covered with an empty cup. Okay, pour it around half full, not much over half full if you do a little bit. That's okay. Okay, dump the rest of that so you don't get them confused. Okay? And take the mass of the water. How much?
Did you stand exactly right there? I thought you were talking about the outside.
Okay. Let me give a hint here. I think we did this on the first time we did something with these. These scales go up to 500 grams, I think, right? So if you're reading a 50 somewhere down at the bottom, that's either 250, 350. It's not 50. Okay, be sure you include the first digit. Okay, once you've gotten your mass, you got it?
Yeah.
Flip this over the top, and then take it and put your thermometer in it. Take it. Okay? Okay. All right. Everybody got the mass of the water at the bottom of page 1. That would be calorimetry, Roman numeral 2, A, and the temperature of the water, Roman numeral 2, B, right? Okay, as soon as you got the temperature, take the thermometer out and put a cup over it. You don't want it sitting there. Take it off the scale. You don't want it to fall off the scale. Okay? You recorded the temperature, right? Okay, put a cover it, with a clean cup. No water in it. Yeah, okay. Okay, now, take you another cup. Okay? All right. Place another styrofoam cup on the scale. 0 the scale. And zero the scale, okay? And then take a UQ device and put in it. And it says here, okay, how much you got? Do a little bit. 50, okay, that'll do. Okay? Now take that ice and put it in that. You record your mass. Did you record it exactly or about 50? Okay. Get it as precise as you can. At least. See what you get up here. A little more. Okay, read the maps and dump that in the water. Put around 50 grams of water, somewhere around 50 grams. Okay? As soon as you got the mass of that, remove the top cup and pour the ice into the water. Yeah, put it in. Okay, you got around 50 grams. Okay, put around 50. That's good, that's good. Okay. Record that, you give it to somebody else. Take it off, record your measure, and take it off the scale. And one scale is good. As soon as you got it. Okay. So every team has done this so far. Okay. Oh, you still looking right? Okay. Okay, pour that into your water. Record that, pour it into the water. Put about 50 grams, more or less, that's okay. What's that? Okay, yeah, put the ice in the water and put the cup over the top. Okay, put the cup over the top. Put the cup over the top. Yeah. Wait. Okay. While we're waiting for all that ice to melt, you're not going to take the temperature of the water until all the ice is melted. Right? Okay. Is it all melted? Yeah. You sure? Okay, then you take the temperature of the ice water. That's part B. Okay? Now, while you're waiting for your ice to melt, let's go on down to 4, which really should be 3, but I misnumbered it. Number 4, come up here. If you're waiting for your ice to melt, come on up here. Or if you've already taken the temperature of your water, are you recording the temperature of the water? Okay, record that. Okay? Then come up here. Okay? Everybody. If you're at a place you can come. Okay? Jumping down to 4, bottom of page 2. Here we have some metal rods, and here we have some plastic rods. Now, plastic rods keep disappearing. I don't know where they're going. Okay? Now, they've been sitting in here in the room for many hours. Okay? So, tell me, do you think they're about room temperature? Yes, they would be, right? Let's see what room temperature is. Now, this is in Fahrenheit, but it says 71 degrees Fahrenheit. Sorry to use Fahrenheit. Okay? And you think those, both of them, the estimated temperature of the metal and the plastic is 71, right? Okay. Then come over here, pick up one of each, and hold it to a facial cheek, and see which one feels warmer or cooler. Huh? Not colder, it's the same temperature. Well, which one feels colder? Well, try it. Convince yourself. Okay? Everybody can do it. You don't have to hold it long. Okay? There's plenty of them up here. Everybody check it. Okay? Everybody check it. See what you think. Which one feels warmer? Okay? That's what you think? Make sure. Okay?
What do you think?
I have to hold it long to see which one feels cool. Warmer, sorry. Okay?
No.
Okay, everybody's holding a plastic rod and a metal rod to their cheeks and seeing which one feels warmer. Everybody done it? Okay. Which one did feel warmer? Okay, why? Why does the plastic feel warmer when you're convinced they're at the same temperature?
Less conductive.
It's which?
Less.
Yes, it's less of a conductor. The metal rod is a great conductor, probably aluminum, a very good conductor, whereas the plastic rod is not a good conductor. So therefore, what you're feeling when you hold it to your cheeks, the metal rod is pulling the heat away from your cheek, conducting it to try to get all the rod up to that temperature, whereas the plastic is rapidly coming to your skin temperature. So basically, what you're feeling on the metal rod is 71 degrees, and what you're feeling with the plastic is close to your skin temperature, 95 or something like that. So that's why it feels colder. They're both the same temperature, but the plastic does not conduct the heat away, whereas the metal does. Okay, now let's go back to D. If you haven't done it already, remove the top thing, see if all the ice is melted. If it has, put a thermometer in and measure the temperature of the iced water. There should be no ice in the water. What do you find the temperature to be? Record it. Okay. As soon as it seems to come to equilibrium, record that. Don't let it sit there much longer than necessary. Let it come to equilibrium. What do you find it to be? You got it? Everybody recorded it? Okay. All right. All 5 teams have recorded the temperature of the ice water. So you've got everything filled out from on page 1 and C and D on page 2. Right? Everybody. Okay. Now, number E on page 2, it says write the equation to determine, okay, let's talk about what's happened here. On part 2A at the bottom of page 1, you have a mass of water, right? And a temperature of water. What you have on D is a temperature of partly that water, but after you added ice to it, right? Now, is D all water, or is there any ice still in it?
D's all water.
All water, okay? So, what happened to the temperature of that water that was on B, by the time it got to D?
Cooled down.
It cooled down, okay? So what we want to do is write the equation to determine the heat loss of the original water to determine the total heat loss. Okay, that sounds redundant, doesn't it? What formula would you use there? A little louder? What formula? What represents heat? Q. Q is equal to M times C times delta T. Okay? Now the M for the original water is your number A, right? On page 2, mass of water, 2A. Not 1A, 2A. Mass of water. That's your M. Right? Okay? What your C is what? What does that C represent? Say again? A little louder, I can't hear. No. T is temperature. What is C? What kind of heat? Specific heat. And what is the specific heat of water?
1.
1.00. What units?
Celsius.
Say again?
Celsius.
Okay, that's a temperature measure. Heat is measured in? Calories. So it will be calories. The C is 1.00 calories per gram degrees Celsius. Okay? The mass was in what units? What did you? Grams. Okay, this mass is in grams. Okay? Okay, what's your delta T? That original water started at some temperature and ended up at what temperature? A different one, right? D. Take the difference of those two, that's your delta T. Right? Got it? So you got your delta T. That's going to be depending on what? Your mass goes here. There's C. The delta T goes here. You're going to multiply these three things together. Understand what we're talking about? Your grams, that was on 2A times C, which is 1 calorie per gram degree Celsius, times, what's your delta T? That's the difference between 2B and 2D. Or just not to be. Everybody got it? Or getting it? Okay. Let me see what your numbers are looking like. You got an answer? Oh, yeah. No, it doesn't matter. Either one. Just so, as long as you got your units, it makes sense. Everybody got an answer? Want me to see if it's reasonable? You don't have to cover it anymore. You've already done it. You can dump it out. Okay, you got the number? You good? Okay. Okay. Once you got a number, let me see to make sure you're not out to lunch.
The one.
That doesn't seem right.
Grams is your
Okay. 278 grams times 1 times the change in temperature, which is 15. That's times. That's a times. No. Your change of temperature. You started at 42, you wound up at 27. What's the change of temperature? That's your delta T. Whatever that turns out being. And then times 1, but most of what the 1 gives you is that's your delta T. So that's what you put here. The mass here times 1 times that. Delta T. Everybody got an answer?
I think I gotta put that unit on.
Okay.
That's
That's your mass. 1, yeah. Grams per calories per gram. Okay, that's what you got. So you started off 40 and 1 level 20, right on the nose. So that would give you, see, suspicious, but okay. That gives you a change of temperature of what? 20 degrees. So that's what your delta T is. So your mass is C was 1, delta T is 20. Multiply those two together. Everybody got an answer? Do you want me to see an answer? That was okay. So I can find it. And what units will that be? Okay. What were our units here? Calories per gram degree Celsius times grams. That'll cancel out the grams. This will be degrees Celsius. That cancels that. Your number comes out in calories. Now, if you move your decimal 3 places, we can make it kilocalories without calories or fire. Okay? Every team got an answer? Let me see it. That sounds beautiful. What you said? Do the calculation. What's that? In calories. That gives you your delta T. Got it? That's the formula. That's the equation. Right there. Write it down. From the equation. Where it says equation. That's where you write it down. Okay. That's this one. This equation. That one. E. Right there. Write it up there. Q is equal to MC delta T. Does everybody understand that? On E. There's two parts to E. The first part is the equation. There it is. That's the equation. Write that down. The second part is when you put in your numbers. Your mass was from 2A. Your C, I wrote down for you. The delta T is the difference between 2D and 2D. The difference. That's what delta stands for. The difference between those. And then you multiply those three numbers together with the unit. Okay? Everybody got it? I need to see an answer from everybody. I've seen, I think, most groups, what you get. Exactly on the note. Pretty suspicious, okay? You may be right on. So I'm guessing you said, oh, that's about. You were right on 20 degrees. Right on 40 degrees. Okay. And right on what was your mass, by the way, for that first water? Huh?
250 grams.
Right on the nose.
Yeah.
You all got your answer? Yes. Got the answer? Yes. Huh? You got your mass? 590 grams? Sounds bad. Now the equation you should write there is that equation, LC delta T. Okay. Okay. And then you plug in the value. So you can write that down too if you want to. You can have them both down there. That's the equation you use. What was your delta T? You can calculate that. Okay. Okay. I need to say a number from everybody. Have I seen somebody, a number from each team? Huh? D is where you started. Right? E. 29. What did you straight to? 11 degrees Celsius. Huh? Okay. Then multiply those this out. Mass times basically. The other thing, one, okay. So if you get a number, let me see your number. Y'all got a number yet? Okay. What unit is first? Okay. What unit? Calories. Exactly. It's grams times calorie per gram degree Celsius times degree Celsius. The grams cancel out, degree Celsius cancel out, leaving you calories. Okay? Right? All right. Okay, that was E. All right? That was the heat loss from the warm water going down to the iced water. Just that warm water to iced water. Okay, I'm still recording, right? Now, the F part says, write the equation to determine the heat gained by the melting ice. Well, this is the one I gave you right at the end of class. As ice melts, what is the heat gained by the melting ice? What is happening there? Are you changing temperature? No, huh? You're just melting the ice. So what do you use there? Your Q for this gain. This was heat loss. This is Q gain. And this is Q gain from melting. I gave it to you right at the end of class today. We stayed a little longer so I could give it to you. What's that formula? You got your books? It's in there.
Q equals M.
It's what? Q is equal to? M times what? L, exactly. Q from the melting ice is the mass of what? The water? No, the ice. Mass of the ice, this is mass of the water. This is mass of the ice times your L. Which L are we using here? LF, because that's the latent heat of fusion. Okay? So you got the mass of the ice. You recorded that on C, 2C, top of the second page. And what is your latent heat of fusion? Does anyone remember? It's in your book if you brought your book. 80, exactly. The latent heat of fusion is 80.0 calories per gram. Calories per gram. Multiplied by your grams, whatever your mass of ice was, that gives you calories. Okay? Everybody got it? Pretty straightforward, huh? You got it? Everybody got it? Once you have a number, let me see it.
You said that's the mass of ice?
Okay? Say again?
You said mass of ice?
Mass of the ice. Exactly. Okay? Yeah, sounds reasonable. Anyone got a number? Yeah. Go. What's that? Where'd you get? Is that the mass of the ice? Exactly on the nose.
Yeah, I put that exactly. You say it would do. Looks like you're 49.
Well, if you want precise answers, you gotta have precise answers. Y'all got it? Yes. Have you got a number? Again, 4,000 calories on the nose. Okay? Y'all got a number yet? How much? Really? Yeah, put that equation there, the one I wrote on the board. The equation I wrote on the board. The one on top goes in E, and the one on the bottom. Now you can put the numbers there too, but I want that equation. Okay. Right here. $4,000. That's a lot better than 400.
Still alive.
Yeah. I can see.
I would not.
How did your first one come out to be?
Don't do shit about work. 'Cause brothers Dustin great to a teacher.
All right. Everybody got a number? All right. Look, when I take my parts to the shop, y'all round down just like you did. Okay. Okay. Now, does everybody have a reasonable number for F? Right? Okay. Now listen up. All of you got a number for F. You got this equation and some number. And that number should be a little bit less than the number up here for E, right? Okay. Now, let's look at G. Okay, think about what's happened now. You had warm water that cooled down to cooler water. That was this delta T right here, right? Then you had ice that melted. Ice, and now here's the assumption here. We're going to assume the ice was at 0 degrees to begin with. Because it had been sitting out in the room, it probably was just ice. It wasn't probably down at minus 20 or something. When I got it out of the ice machine, it may have been cooler, but I let it sit here a while. It probably comes to pretty close to 0. Okay? And you melted that ice. Once you melted it, what was the water? It melted from solid to liquid. What was the temperature of that water? Don't look on your page. When you melted the ice, just the ice, what was the temperature of the water? 0, because there's no change of temperature here, right? Now you're heating that melted ice. This is what G is doing. Write the equation to determine the heat gained by the melted ice water and calculate the heat gain assuming it started at 0 degrees Celsius. So you see, when you melted this, I know it immediately came up to the oven. But when you melted it, there's no temperature change. So that melted ice is now at 0 degrees, water. 0, right? And now you're warming it up. So you're using this formula here, except now it's a heat gain, not loss. And now it's the mass of the ice water. This same ice mass here that was ice is now liquid. So it's that mass and then your delta T. But this delta T is from 0 to whatever your final temperature was. Right? That's your change of temperature. That's a heat gain. You warmed it from 0 degrees up to whatever you recorded in D. Okay? So your equation is the same as the top one, except, I'll write it down. The third one is Q, G, and this will be of the water. Okay? The heat gained by the, I'm going to put ice water. Okay? And that would be the mass of the ice water, same as the mass of the ice, times C, because it's water again, right? It's not ice anymore, it's water. So that same C, but this delta T was the delta T that went from 0 to whatever the final temperature was. So it's a different M from up here and a different delta T from up here, except maybe from this group over here who had everything being the same. Okay, no, I'm just kidding. Okay, sort of. Okay. Okay, any questions? I can help if you have questions. If you have an answer, let me see your answer. Okay? Really, what I want to do is leave the numbers in there. Write it up. What those equations are. Leave what you got. Write it above. Why do you got use that?
Okay, so we do, so we.
One, 2, 0 stays the same. That's right.
Just the,
Okay. The 50 grams. Okay. Times 27 because it started at 0 and up to 27. Or whatever that means. That is the delta T you use here.
yeah.
Yeah. Except it's a different mass and a different delta T. That mass is the melted ice, so it's not 250 anymore, it's 60. And yeah, your delta T, as always, is 20. Okay. But it's this 20. 20 minus 0, not 40 minus 20.
Okay.
Because you're warming up the melted ice at 0 up to this point. Okay. Before you were cooling down the water at 40 to that 20, which comes from around the melt. Never mind. Okay. All right. After you've done that, add your two gains together. How are y'all doing? Got an answer yet? Okay. Anyone who's got an answer yet? Okay. What you do now is add those two together. Y'all got an answer yet? Okay. What you do is add these two together and your total heat. Okay. How are y'all doing? Got answers yet? And then you can add these two together, see what you get there. And Of all the groups, I think have reported. Okay. Now, if I didn't tell you when I was at your station, you can add F plus G, the heat gain melting and the heat gain warming, to get your total heat gain, which is H. Right? Okay. Have you got your,
Yeah, we got it outside.
okay. This is the gain. That's the gain. Yeah, these together you get that. Okay. Okay. Everybody got an answer? Okay. Now, everybody has added and got everything through H, right? Yes? Everything through H. Okay? Number I, or letter I. Compare the heat loss with the total heat gain. You're comparing E, the second blank in E, to the blank in H. Okay? It says, what's the difference? Subtract the smaller from the larger. That's the difference. Understood? Okay? Which of these is larger? Heat loss or heat gain? Heat gain? Okay, some groups may be gained, some may be lost. Okay? Now, what I want you to do, just for fun, is take that difference that you calculated for I1, first blank in 1, divide it by let's do the heat loss. Okay? And you don't, there's not a blank for it, but I want you to record, tell me what that is. When you divide the difference by the heat loss, put it on the calculator, let me see what it is. Okay. Now this isn't anything you have to write down. Yes, you're 6%. That's pretty good. Okay? Anyone got it? What you got? Okay, 26%. Where were you that far off? Okay. Got it. Well, actually, divide yours by the heat gain. So 1,080. Pretty big difference. Divided by the heat gain. So 21%. Huh? 2%. Rounding sometimes helps, right? Okay. I got it. Okay. Okay, let's talk about the why. Okay? Now, which one was larger, heat loss or heat gain? Okay, y'all had heat gain. Okay? What was your final temperature? 25. Okay? 25 degrees is actually warmer than the room temperature. Room temperature is right around 69, 70. Okay? So probably you gained some heat. No, that would be going the wrong way. What was your percent?
21%.
I would say experimental error. Okay? I can't think of a reason for it otherwise. Which was larger for you, heat loss, or heat gain? Okay. So I'd say experimental error is the only thing I can think about. Okay? Basically, here's the deal. If your if your final temperature was warmer than your room temperature, then you expect to lose some from the cup to the room. If your final temperature was cooler than the room temperature, you expect to gain some from the room. If you don't get that, you probably just experimental error. And when your numbers down around 3, 4, 5, 6%, yeah, that's just a little. You're so close, it doesn't really matter. When you're up a little bit higher, it's an experimental error. Okay. And some people just have too close. Okay. All right.
We're just born to be scientists.
All right. Mad scientists, I would say. Okay. All right. How'd y'all find this lab?
One for today, and then one for.
Oh, okay.
I got one.
No, just leave them on the table. I'll get them. Dump all your waters, if you will, please, and turn the cups upside down. Thank you. Okay. Y'all ready for it? Y'all ready? Even with your name? Wow. Okay. All right. Let's move back to the classroom. Okay. Any questions about the lab? I'm going to go and shut this down and let it be uploading. You can go back